All right, let's get right into it. Welcome to this explainer. So if you're a college student staring down the barrel of a basic electrical engineering course, or maybe you're just someone curious about the technology we rely on literally every single day, either way, you are absolutely in the right place. We are going to completely set aside that fast-paced academic anxiety today. Instead, we're going to take a calm, structured look at the foundational concepts of electricity. Just think of this as your peaceful guide to understanding the invisible world that powers our modern lives.
I mean, take a quick look at whatever device you're using to watch this explainer right now. Whether it's a smartphone nestled in your hand or a laptop sitting on your desk, there is this silent, invisible storm of energy working furiously behind that glass screen. What exactly are those invisible forces? How does a relatively small, silent block of chemicals, your battery, manage to bring a complex machine to life, rendering graphics, playing audio, and connecting you to the whole world?
Let's just take a collective deep breath. Seriously, in academia and especially in engineering, it is so incredibly easy to get completely lost in a sea of complex equations and terrifying calculus before you even understand what you're actually calculating. Today, we're stepping back from the intimidating math. We're going to build a genuine, intuitive understanding of these ideas from the ground up. The math will always be there later, for sure, but first, we need to understand the story.
All right, let's kick things off with Section 1, Charge and the Flow.
Before we can even talk about how a battery works, we kind of need to know what it's actually pushing around. And that all starts with electric current. By definition, current is the rate of flow of electric charge, which we measure in amperes. But let's build an intuition for that, rather than just reciting a textbook. Imagine a massive invisible river. Instead of water molecules, this river is made up of countless tiny particles called electrons. When these charged particles start moving together in a specific direction over a period of time, we call that movement a current. It's really just the flow of charge.
And here's how we actually write that down in engineering. You see that formula? I equals dq over dt? Now, if you've taken calculus, your heart rate might have just jumped a little bit. But hey, don't panic. Treat this formula purely as a visual model. The little d there just means a tiny little change in. So this simply says that current, the I, is just a tiny slice of charge, the dq, moving past a point over a tiny slice of time, the dt. It's literally just measuring the speed of our invisible river.
But a river needs a riverbed, right? Otherwise, well, the water just spills everywhere. In electricity, that riverbed is our conducting path, usually a copper or aluminum wire. You can see how this diagram perfectly illustrates that these charges are confined to conductors. Just as riverbanks hide the water, the insulation around our wires prevents these charges from leaking away from where we want them to go. And we call these contained, guided paths circuits.
Which brings us to Section 2, the push of potential.
Think about it. Water in a real river flows down a mountain because of gravity. But what makes our invisible river of electrons start moving through a wire in the first place? They don't just, get up and move on their own. They need a push. And that push is what we call electromotive force, or EMF for short. Electromotive force is exactly what it sounds like. It's the force that motivates electrons to move. It's the electrical potential difference between 2 points that actually causes a current of electricity to flow.
So, the absolutely crucial thing here is getting the difference between these two foundational ideas. Let's contrast them directly to really lock in that intuition. Electrical current is the flow itself, the actual physical movement of the charged particles through the wire. Electrical potential, which you'll often hear called voltage or EMF, is the pressure or the push that forces those particles to move. Basically, you cannot have the flow without the push.
And this is exactly where our battery enters the story. If you look at the definition of EMF here, it reminds us that this push is the defining characteristic of a battery. A battery is essentially a pump for electrons. Through some really cool chemical reactions happening inside its casing, it creates a high potential at one terminal and a low potential at the other. When you connect a wire between them, bam, it provides that vital electromotive force to push the electrons right through your circuit.
Moving right along to Section 3, Work, Energy, and Power. Okay, so now that we have a push and a flow, we can actually start doing stuff. Because, let's be real, the whole point of a circuit isn't just to move electrons around for fun. It's to harness that movement to do actual work in the real world. When our battery pushes that current through a device, it's doing work. And we measure the rate of that work as electrical power. Power is simply how fast a battery can do its job. Our sources define it beautifully as the product of voltage, the push, and current, the flow. Think of a powerful fire hose. To get maximum power, you need both high water pressure, the voltage, and a super wide pipe for lots of water flow, the current. But wait, here's where it gets super relevant for your everyday life. We really need to clarify the difference between electrical power and electrical energy. Power is the rate of doing work right now. It's the brightness of your screen at this exact literal second. Energy, on the other hand, is your total capacity to do work over time. So when you're looking at that little battery percentage icon on your phone, you are looking at its remaining energy, not its power.
Check out these shorthand models for a sec. We've got P equals VI, power equals voltage times current. Again, push times flow. But right below that, we see W equals PT, energy equals power times time. This is a hugely important characteristic for batteries. A battery's total energy capacity is really just its power output multiplied by how long it can sustain that output before running out of chemicals to react. It's essentially the total amount of water sitting in the water tower, just waiting to be used.
All right, let's look at section 4, the circuit's cast of characters.
So the battery provides the energy, right? But who's actually using it? Engineers like to organize these circuit components into a pretty gentle hierarchy. You can see how this classification tree divides our cast of characters into two main groups, based entirely on their relationship with energy. You got those that give it, and those that take it.
First up, we have the givers. In engineering terms, these are called active elements. An active element is a component which actually supplies energy to the circuit. It is the engine, and as we've been discussing, voltage sources, like our trusty little battery, are the prime example of active elements. They serve as the heartbeat, constantly supplying that vital electromotive force to the entire system.
And on the flip side of that, we have passive elements. If active elements are the ones giving the energy, passive elements are the ones receiving it. They don't generate power themselves. Instead, their job is to either consume that energy to do work or to temporarily store it up just to release it back into the circuit a fraction of a second later.
Take a look at these passive characters, resistors, inductors, and capacitors. Think of them as the workers in a factory. The battery provides the energy, but these passive elements are the parts of the device that actually use it. Resistors dissipate energy, maybe turning it into heat or light. Capacitors and inductors, well, they store energy in electric and magnetic fields. Together, they take the raw push from the active battery and completely translate it into the lighted pixels on your screen or the music coming out of your speakers.
Finally, let's wrap up with section 5, a peaceful closing thought.
We've definitely covered a lot of ground today, but hopefully the whole thing feels a bit less intimidating now. Let's just zoom out from the individual formulas and parts for a second and look at the system as a whole. Our source notes feature this incredibly grounding quote. An electrical network is the interconnection of many electrical components, such as sources, resistors, inductors, and capacitors. And really, that's all it is. Whether it's a simple flashlight or the incredibly complex logic board of a supercomputer, it is fundamentally just an interconnected family of active elements pushing energy and passive elements receiving and transforming it.
So if you are a student stressing over a tough exam, just remember this low-pressure takeaway. The math is literally just a model. Those complex circuit diagrams, they're just maps. The underlying reality is beautifully simple. A battery provides the push. The electrons flow. And that energy is never lost. It simply transforms from chemical energy in the battery to electrical energy in the wire to the light, sound, and data that enrich our everyday lives.
We've unpacked the current, the voltage, and the key characteristics of the battery that make the whole shebang possible. So I want to leave you with a final thought to chew on. Next time you plug in your phone or boot up your laptop, how will you picture that invisible river of energy flowing through it? Keep that curiosity alive, and until next time, keep learning.